Welcome to my channel Education Shop. In this video, solve example 11.2 from the book Heat Transfer by A.Çengel, 6th edition. This is example 11.2 from the chapter of heat exchanger. A double pipe shell and tube heat exchanger is constructed of a stainless steel whose thermal conductivity is 15.1 watt per meter Kelvin. Inner tube of the inner diameter is di, that is 1.5 centimeter, and outer diameter is d naught is 1.9 centimeter, and an outer shell of inner diameter is 3.2 centimeter. Convection heat transfer coefficient is given to be Hi, that is 800 watt per meter square Kelvin on the inner surface of the tube, and on the outer surface of the tube is 1200 watt per meter square Kelvin. The fouling factors, that is RFI on the inner side, that is 0.0004 meter square Kelvin per watt on the tube side, and RF fueling factors outside of the tube is 0.0001 meter square dot Kelvin per watt on the shell side. Determine the thermal resistance of the heat exchanger per unit length and the overall heat transfer coefficient UI and U naught based on the inner and outer surface area of the tube respectively. Shell and tube heat exchanger, and this is the zoom out picture. In the zoom out picture you can clearly see that the fouling factors inside and outside of the tube. This is the tube in which hot fluid is flowing. This is the tube and it is enclosed in a shell. In shell the cool fluid is flowing, and in tube the hot fluid is flowing in this direction and the cool fluid is flowing in this direction. So the flow is basically the cross flow. Let me write the data that is provided in the statement. First of all, the material from which this heat exchanger is made up of stainless steel whose thermal conductivity is 15.1 watt per meter Kelvin. Now the inside diameters of this tube is di, that is 1.5 centimeter. The inside convection heat transfer coefficient of this tube in which hot fluid is flowing, that is 800 watt per meter square dot Kelvin. Next is the fouling factor of the inside of the tube, and this is the tube in which hot fluid is flowing. Inside there is some resistance to the heat transfer is occurred because of the fouling. The debris, fouling is nothing, it is the debris sediments of the fluid that is deposited on the tube wall inside and outside. That's why the fouling factor is provided inside of the tube and outside of the tube. So prove the fouling factors inside of the tube is RFI and it is 0.0004. Next is the outside diameters of the tube, that is d naught is the outside diameter of the tube, that is 1.9 centimeter. The outside convection heat transfer coefficients of this tube, here the convection heat transfer coefficient of this cooled fluid that is given H naught and it is 1200 watt per meter square dot Kelvin, and the outside cooling factors of the tube is RF naught and it is 0.0001. What we need to calculate in the first requirement is to find the thermal resistance of the heat exchangers per unit length. The length should be considered 1 meter and we need to calculate the thermal resistance of this heat exchanger. In the second case, we need to calculate the overall heat transfer coefficient based on inside of surface area of the tube, and we need to calculate the overall heat transfer coefficient based on the outside of surface area of the tube. Now let's come toward its solution. In order to find the thermal resistance of this heat exchanger, we need to draw the thermal resistance network diagram for it. In this way you will clearly understand how much resistance are there in heat exchanger when there is a fouling factor. Let's consider first, let's consider this zoom out picture. The hot fluid is flowing in this tube. Let's say the temperatures of this point is T infinity 1 and the temperature at this point is, let's say, T infinity 2. This is, let's say, inside temperatures of the hot fluid, and this is the temperatures outside of this tube, that is T infinity 2. First of all, the heat is transferred within the tube from this point to the surface of the tube, and the mode of heat transfers occur in the tube is convection heat transfer, and the resistance offered to within this tube is, let's say, Ri, because of the inside convection heat transfer. Now and we also know that there is some fouling inside the tube. Fouling means some sediments and debris inside the tubes. It offers some resistance to the heat transfer, and that is, let's say, R1, and then resistance is offered to the heat transfer by this tube wall thickness that is in the cylindrical shape, that is R2, and then resistance is offered to the heat transfer by the fouling outside the tube, that is R3, and then heat is transferred from this point to this point, and the type of resistance to the heat transfer occur is R0. So in total, how much resistance is offered? That is Ri, R1, R2, R3 and R0. Let me draw this thermal resistance network diagrams below. for this heat exchanger. First is the temperature, T infinity 1. First resistance to the heat transfer is Ri, that is because of the convection heat transfer inside the tube. Then R1, resistance offered to the heat transfer because of the cooling factor inside the tube. Then R2, resistance offered by this cylindrical tube wall to the heat transfer. Now again the resistance to the heat transfer offered by the cooling factor outside the tube. And then again convection heat transfer outside the tube, that is R0. And finally the temperature reaches to T infinity 2. Here the temperature is T infinity 1. If you see from this thermal resistance network diagram, the overall thermal resistance of this heat exchanger is simply the addition of R1, Ri, R1, R2, R3, R0. What is Ri? Ri value is equal to 1 divided by HIAI. We need to calculate the internal surface area of this tube, that is equal to pi DIL. Pi, what is Di? That is 1.5 multiplied 10 to the power minus 2. This guys, it is in centimeter. To convert into meter, it is equal to 1.5 multiplied 10 to the power minus 2 meter. Similarly, the outside diameters of the tube is 1.9 multiplied 10 to the power minus 2 meter. And the length is 1 meter, and you simply multiply this, you will get the inside surface area, that is equal to 0.0471 meter square. Similarly, the outside surface area of the tube is equal to pi d naught L. What is d naught? That is 1.9 multiplied 10 to the power minus 2, and the length is 1. You simply multiply and you will get it outside surface area, that is 0.0597 meter square. Put in this value, Hi is 800, inside surface area is 0.0471. Convection, it will give you the Ri resistance to the heat transfer, that is 26.5 multiplied 10 to the power minus 3 Kelvin per watt. Next is R1. R1 is the resistance that is offered to the heat transfer by the inside fooling of the tube, that is Rfi divided by inside surface area. You simply solve on calculators and you will get R1 value, that is equal to 8.5 multiplied 10 to the power minus 3 Kelvin per watt. Next is R2. R2 value is the resistance offered to the heat transfer by this cylindrical tube, ln d naught divided by di divided by 2 pi kl. Ln, what is d naught value? That is 1.9, and di value, that is 1.5 divided by 2 pi. K value is 15.1 and L is 1. Now just simply solve this on calculator and you will get the R2 value. Let me solve it. That is equal to almost 2.5 multiplied 10 to the power minus 3 Kelvin per watt. Let me write on the notebook. Next is the resistance that is offered to the heat transfer, is the R3 value. R3 is nothing but it is the resistance that is offered to the heat transfer by the cooling factor outside the tube. That is Rf naught divided by outside surface area of the tube. The Rf naught value is 0.0001. Outside surface area is 0.0597. I solve this on calculators and you will get the R3 value. Next is the final resistance that is offered to the heat transfer is R0, and that is equal to 1 divided by H0 N0. When you solve this on calculator, you will get the R0 value. It is equal to the total resistance is equal to Ri plus R1 plus R2 plus R3 plus R0. Simply add it and you will get the total resistance, total thermal resistance value you will get, that is 53.175 multiplied 10 to the power minus 3 Kelvin per watt. And this 10 to the this 10 to the power minus 3 is basically equal to milli. In other words, I can also say that the thermal resistance value is equal to 53.175 millikelvin per watt. This is M, sorry. Now let's come to the second requirement to find the overall heat transfer coefficient based on the inside surface area of the tube, that is equal to 1 divided by RAI. 1 divided by R value. R is 53.175 multiply 10 to the power minus 3 multiply inside surface area, that is 0.0471. just simply multiply and you will get the overall heat transfer coefficient based on inside surface area is 399 watt per meter square Kelvin. Next is U naught, that is 1 divided by R A naught. The A naught value is 0.0597. Simply multiply and you will get the U naught value, that is 315 watt per meter square Kelvin. And this is our final answer. I hope you understand. If there is any revision, you can ask in the comment section. Please subscribe my channel if you haven't subscribed. Thank you so much.